we have to go from source to destination such that the target should be equal to it, and that target should be the shortest path always. Where my intuition failed was I did not see that the shortest path after I changed the edges might not be shortest path in itself if I make it to target. I was always trying to make it to target. I was not even trying to find the shortest path in the first place. I was trying to find the shortest path, making those edges as 1 and 1, and then just dumping the last edge with x, which made it a variable, and that particular shortest path failed. So this problem is very analogous to road planning or a development in the city, wherein a city has already some roads already constructed with some predefined length, and we need to create some more roads between cities which are -1 representations with some length x1, x2, x3, and that x can vary from 1 to 2 into 10 to the power 9 according to the question. And when we fill in those with some values, we have to make sure that the shortest distance from the source to the destination becomes equal to target, the shortest destination, shortest path. So there can be 3 cases over here. One is just calculate what is the current shortest distance, neglecting all the -1s. If I don't consider the -1 as an edge only to reach the from source to destination, then you have to just find out the shortest distance, and then I'll check if the current shortest distance is already less than the target, right? Then we can for sure know that there is no possibility wherein we have to return the empty array only, because there is no possibility how much ever I change the other -1s, this will be the shortest path, right? Like no matter how much ever I change the -1s and make it reach target, right, some path equal to target, but this shortest path will always be the shortest path. This target path will never be the shortest path. Even if I end up making a path which equals the target, this will never be the shortest path, right? This is where my first solution also failed. Now second thing is when the current shortest path is equal to the target, so the problem will boil down to, suppose if this was the shortest path, right, in the whole graph, then we first check if it was less than the target. If it was less than target, we can just return an empty array. If it was equal to target, do we like now do we care about the other roads? We can just mark it as 10 to the power 9s, so that other edges will never make it a shortest path. Let this only be the shortest path, right? We already have the shortest path, we don't care about the other -1, but we have to change it, so just change it to 10 to the power 9. Coming to the third and the main one, like if it was greater, if this path was itself, suppose the target was 4, to reach quantity 4 we cannot have this one, right? We have to somehow change these -1s only internally to make the from here to here via this route as 4. What can we do? We first start transforming -1 to 1, and then check whether this transformation made a shortest path from source to destination which is less than or equal to the target. If it did, then we again don't care about anything else, right? Others, everything can be marked as 10 to the power 9s, so that they don't make the shortest path. We already have the shortest path which is equal to target. If not, we go to the next -1 and then change that -1 to 1, and then check again run a shortest path in the whole, run Djikstra and get the shortest path between source to destination with this as 1. Now why only 1? 1 is the shortest value that we have, right? And we want the shortest path. Now I found out that sometime that the shortest path is less than or equal to the target. Now I know that this path gives me a value which is less than or equal to target. If it is equal to target, very well and good, others everything can be marked as infinity, right? But if it was not, then the last road that I changed to 1, I have to also account for target minus this shortest path value, right? So whatever is the length in that has to be accommodated in this only, so it will become 1 plus this target minus shortest path, this road's length. Apart from this, again another every minus ones will just become 10 to the power 9s. So again we can just see the code. Djikstra is simple. Djikstra, I feel like it is just another way of saying we run a BFS, and then that is a like in my understanding, Djikstra is a modified BFS wherein we use priority queues to find the best possible answer, best possible scenario, best one which makes it greedy, right? And then Djikstra we do a traversal. Traversal is done in some way, and that traversal is using queues, right? Traversal using queues, which is a priority queue, which makes it a BFS. We go by like the breadth first, right? But not exactly BFS. BFS is analogous, we can say, because we do not go layer by layer. We do not explore every possibility in that layer. We just explore the best possibility out of all the present variables that we have. So BFS is also present. Then the next thing I could say that the distance array. I need to have the distance array, right? Which makes it kind of a maybe DP, I would say, because we are storing the previous states to get the next state, right? We are storing some previous states, we are initializing some states, and then we are going from the lower truth to the higher truth over here. So it is a DFS. So Djikstra is basically a modified BFS with greedy approach using dynamic programming. So this is my definition of Djikstra, like how I want to remember it whenever I see this video. Next thing is, we can just look at the code. Djikstra code is simple. We just make the graph first, keep the initialize the priority queue and the distance arrays, and then put the first element into the priority queue, remove the first element from the priority queue, explore its neighbors, push again into the priority queue if it meets the criteria that it lessened the distance of the particular node, and then at last we can just return the destinations, but it will never generally come here. Over here only it will go back. This is important because the first time Djikstra reaches a node, right, which means that for that node we have found all the shortest path. We have shortest path, and then it can never be less than the shortest path if we have reached already that node and we are trying to explore its neighbors. First time removal. There was another question that the second time removal was required where we needed the second shortest path. That was another question which I don't know if I documented it or not. But the next thing is, we just first check. This is just a helper function that we discussed. Now Djikstra will give me the current shortest distance. Now after getting the current shortest distance, I need to check the first case. If I check the first case, I'll return with a empty array. Then I will check if it was equal to target. If it was equal to target, I'll just make the matches target as. So this will help us define whether that edge right, which was a -1, should transform to infinity or a 1. So if we have equal to target, right, we can just go to all the edges and check if this match the target already. We don't need to change any other -1s to a 1 and consider the possibilities, which is the third case. We can just instead mark everything as infinity. That only we are doing. If edge is greater, just continue, we don't have to do anything. If edge is a -1 edge, then we consider that If it has already matched the target, just make it infinity, we don't care about that edge. If it was not matched the target, then we have to try to make it match till we can. To try to make it match, we first mark it as 1 and then run the Djikstra, get the new shortest distance. Now this new shortest distance, if this distance is at least less than or equal to target, which means that our try was successful. If it was less than equal to target, then we just make the matches target variable as true. So this will make sure that subsequent -1 edges get marked as 10 to the power 9 to make sure that those subsequent edges do not make another shorter path than this. And then at last, whatever was the final value of edges, we'll be just returning that if it matched the target. If it still did not match the target, after all the tries that we did, we converted all the -1s to +1s and then checked if the shortest distance was possible. If it was not possible, then we just returned this. And if it was possible, whenever it was possible, we just changed the edge of 2 as target minus new distance is the same thing as this. We have to accommodate for the difference between these into the last row that we have transformed.